Hello everyone and welcome to the third video of the MIST102 series. I hope you all are keeping well during these uncertain times. I am Shubhra Bedi and this workshop is focused on reinforcement learning, a very popular type of machine learning technique that enables an agent to interact with the environment. In this workshop, we would be going over what is reinforcement learning, formulating some reinforcement learning problems, and understanding some important reinforcement learning algorithms. We would also look into the practical applications of reinforcement learning along with its challenges, and then end this workshop by summarizing all that we have learned so far in the MIST101 and MIST102 series along with the code demo. In the last workshop, Nick went over recurrent neural network, wherein he talked about sequential data and memory, how memory works for humans, recurrent neural networks, as well as problems with RNN, and finally ending with LSTM and GRU. So let's dive into the topic for this workshop. What is reinforcement learning? Reinforcement learning is a type of machine learning technique that enables an agent to learn in an interactive environment by trial and error using feedback from its own actions and experiences. Reinforcement learning is the training of machine learning models to make a sequence of decisions. The agent learns to achieve a goal in an uncertain, potentially complex environment. In reinforcement learning, artificial intelligence faces a game-like situation. The computer employs trial and error to come up with a solution to the problem. To get the machine to do what the programmer wants, the artificial intelligence gets either rewards or penalties for the actions it performs. Its goal is to maximize the total reward. Although the designer sets the reward policy, that is the rules of the game, he gives the model no hints or suggestions for how to solve the game. It's up to the model to figure out how to perform the task to maximize the reward, starting from totally random trials and finishing with sophisticated tactics and superhuman skills. By leveraging the power of search and many trials, reinforcement learning is currently the most effective way to hint at a machine's creativity. In contrast to human beings, artificial intelligence can gather experience from thousands of parallel gameplays if a reinforcement learning algorithm is run on a sufficiently powerful computer infrastructure. Though most supervised and reinforcement learning uses mapping between input and output, unlike unsupervised learning, where the feedback provided to the agent is correct set of actions for performing a task, reinforcement learning uses rewards and punishments as signals for positive and negative behavior. As compared to unsupervised learning, reinforcement learning is different in terms of goals. While the goal in unsupervised learning is to find the similarities and differences between data points, in the case of reinforcement learning, the goal is to find a suitable action model that would maximize the total cumulative reward of the agent. Let's look into an example of a reinforcement learning, which is a Skinner box, and it's an experiment by B.F. Skinner. In this experiment, at some point, the rat, as you see in the box, might accidentally touch the lever, and depending on the condition, this could lead to the release of the food, which is reinforcement, or charge the electrified grid, causing a shock, which is punishment. Over time, the rat learns which behaviors are rewarded and punished and chooses its actions accordingly, and hence this is an example of reinforcement learning. This example, in which an animal pushing a lever causes the release of a food pellet, would be termed as a positive reinforcement, while an electric shock in return for a lever push would be termed as a positive punishment. Another kind of operant conditioning is when a stimulus is removed based on a behavior. For example, an unpleasant sound may be turned off based on pushing a lever. This would be referred to as a negative reinforcement. And alternatively, the removal of a pleasant stimulus would be referred to as a negative punishment. Now let's see on how we could formulate reinforcement learning problems. Some key terms that describe the basic elements of a reinforcement learning problem are environment, state, reward, policy, and value. What's environment? So the environment basically provides the agent with the current state. It provides a reward at each time step, which is mostly a zero reward. The state is the current situation of the agent. The reward is a feedback signal from the environment, and the goal of the agent is to select actions to maximize total future reward. The policy is the agent's behavior, the action it chooses at a state. It is usually represented with the letter lambda, and the policy function is a function that maps state to action. Lastly, value. Value is a future reward that an agent would receive by taking an action in a particular state. It is done with the help of a value function. A value function is a prediction of future reward assuming we follow a particular policy. It's used to evaluate the goodness or badness of states. The value function is a function that maps state to expected discounted return, and the figure on the side illustrates the action-reward feedback loop of a generic reinforcement learning model. In order to build an optimal policy, agent faces exploration versus exploitation trade-off. The exploration-exploitation trade-off is a well-known problem that occurs in scenarios where a learning system has to repeatedly make a choice with uncertain payoffs. In a sense, the dilemma for a decision-making system that only has incomplete knowledge of the world is whether to repeat decisions that have worked well so far, which is exploit, or to make novel decisions hoping to gain even greater rewards, which is explore. So, looking into some important reinforcement learning algorithms. The agent should collect information about the environment to make the best decision, and to do so, we take the help of few algorithms. They are Markov decision process, which is MDP, QLearning, SARSA, deep Q networks, which is advanced, and deep deterministic policy gradient, which is advanced. So in this workshop, we would be going only over MDP, QLearning, and SARSA. First, we would look into the Markov decision process. The Markov decision process are mathematical frameworks to describe an environment in reinforcement learning, and almost all reinforcement learning problems can be formulated using Markov decision process. A Markov decision process problem is a tuple of S, A, W, P, where S is the underlying state space, A is a set of actions, W, which is a cross multiplication of S and A, which leads to IR, is the cost or immediate reward function, and P of V given UA is the probability that action A in the state U will lead to state V. In some MDPs, the additional costs C incur when arriving at a goal state. The goal is to minimize the expected accumulated cost, or equivalently to maximize the expected accumulated rewards. The Markov property. Our state St is Markov if and only if the probability St plus 1 given St is equal to the probability of St plus 1 given S1 until St. This simply means that the state St captures all the relevant information from the history S1, S2 until St minus 1, which can be discarded, and we can still get the same state transition probability to the next state St plus 1. The state transition probability states that given we are in state S, we can know what the probability of the next state S1 S dash will occur. The Markov process or the Markov chain. It's a sequence of random states S1, S2 and so on with their Markov property that it's a tuple of S and P, where S is a finite state of sets and P is a state transition probability matrix as described in the previous slide. Beside is an illustration of a Markov chain where each node represents a state with a probability of transitioning from one state to the next, where stop represents a terminal state. We can take a sample episode to go through the chain and end up at a terminal state. An example sample episode would be to go from stage 1 to stage 2 to win to stop. I'm going to go over few sample episodes such that so that we can look over the different ways we can go from stage 1 to stage 2 to win to stop. So the three ways we can do this would be directly S1, S2 win stop, or it could be S1, S2 teleport, S2 win stop, or S1 pause, S1, S2 win stop. In the Markov chain, we did not have a value associated with being in a state to achieve a goal. Now, the Markov reward process. The Markov reward process is a Markov chain with reward values. It has a reward process tuple which is SP, R and gamma. SP stays the same from the Markov chain tuple. R is a reward function and gamma is a discount factor. Our goal is to maximize the return. The return GT is the total discount reward from the time step T. GT is equal to RT plus 1 plus gamma RT plus 2 and so on, which would equal to the summation of gamma power k times RT plus k plus 1. The discount factor gamma is a value that can be chosen between 0 and 1. If gamma is closer to 0, it leads to a short-sighted evaluation, while a value closer to 1 favors far-sighted evaluation. This is because lambda to the power k decreases rapidly in value, and if lambda is closer to 0, therefore ignoring the future terms. Now the Markov decision process. This is an extension to a Markov reward process as it contains decisions that an agent must make. All statements in the environment are Markov. In a Markov decision process, we now have more control over which states we go to. Here, if we choose teleport, then 40% time we would be stage 2 and 60% in stage 1. Other state transitions can occur in 100% probability when selecting action advance 2 from stage 2 will take us to win. Now, before introducing QLearning, I would like to draw your attention to what on and off policy is. An on policy agent learns the value based on its current action A derived from the current policy, whereas its off policy counterpart learns it based on action A star obtained from another policy. In QLearning, such policy is the greedy policy. Epsilon greedy is a simple method to balance exploration and exploitation by choosing between exploration and exploitation randomly. The epsilon greedy, where the epsilon refers to the probability of choosing to explore, and exploits most of the time with a small chance of exploring. QLearning is an off-policy reinforcement learning algorithm that seeks to find the best action to take given the current state. It's considered off-policy because the QLearning function learns from actions that are outside the current policy, like taking random actions, and therefore a policy isn't needed. More specifically, QLearning seeks to learn a policy that maximizes the total reward. The Q in QLearning stands for quality. Quality in this case represents how useful a given action is in gaining some future reward. So the first step to approach QLearning would be to create a QTable. So when QLearning is performed, we create what's called a QTable or matrix that follows the shape of state and action. And we initialize our values to 0. We then update and store our Q values after an episode. This QTable becomes a reference table for our agent to select the best action based on the Q value. The next step is simply for the agent to interact with the environment and make updates to the state action pairs in our QTable, which is QState Action as we see here. An agent interacts with the environment in one of two ways. The first is to use a QTable as a reference and view all possible actions for a given state. The agent then selects the action based on the max value of those actions. This is known as exploiting, a concept which was looked into a few slides earlier, and it is known so since we use this information we have available to us to make a decision. The second way to make action is to act randomly. This is called exploiting. Instead of selecting actions based on the max future reward, we select an action at random. Acting randomly is important because it allows the agent to explore and discover new states that otherwise may not be selected during the exploitation process. You can balance exploration and exploitation using epsilon and setting the value of how often you want to explore versus exploit. This in mathematical form looks as follows. This is the QLearning update formula. So the updates occur after each step or action and ends when an episode is done. Done in this case means reaching some terminal point by the agent. A terminal state, for example, can be anything like landing on a checkout page, reaching the end of some game, completing some desired objective, etc. The agent will not learn much after a single episode, but eventually, with enough exploring, that is steps in episode, it will converge and learn the optimal Q values or Q star. Therefore, the three basic steps would be the agent starts in a state S1, takes an action A1 and receives a reward R1. The agent then selects action by referencing QTable with the highest value or by random, which is epsilon, and then it updates the Q values. Now let's look into the frozen lake example to better understand QLearning. So here is a board where S is the starting location, F is the frozen location, H is the hole, and G is the goal location. So this can be better represented by the image. So as we see here, S is the starting, G is the goal, F is all the frozen location, and H is the hole. Here we see that if the agent steps on H, the reward would be 0, and if it reaches G, the reward would be 1. Now let's start computing the QLearning. So here's the formula that we had learned in the previous slide for QLearning, where this is the reward, this is the discount factor, and this is the summation of the state. So if we consider state 1, which is frozen, this would require computing QLearning 1A. So this is a state and this is the action. So for all 4 actions, we would be computing this. So we will take left, right, up, down, and then we set V1 to the maximum of the 4 Q values. So let's start with moving left. So in that case, A becomes L and then we start computing it. And so it's 0.33, that would be the summation, into 0 is the reward because it's F and F is 0, plus 0.9, which is the discount factor, and this is the probability of the next state to occur, which is also 0. So we do this for, we iterate over it, and we just see that the QLearning would be 0, and if we do the same thing for right, up and down, we would again get 0 as its value. So then we're setting v1 to the maximum of the 4 q values, so we would just be setting v1 as 0 because the maximum of all zeros would be 0. And now we would continue to be 0 in all these positions until we get to state 14, where we finally get non-zero values for down, right and up, as well as left. So here we do the computing again, and we see that at one point we get 1 here because it reaches a state where the reward would be 1. So we get the value of 0.33 for down, right would be 0.33, up would be 0.33, and if you calculate for left, you would also get 0.33. So now, since we are taking the maximum value that we store to v, we just see that 0.33 is the maximum value, and therefore v14 would be set to 0.33. Now on iteration, two most values stay 0. However, this time states 10 and 13 also get non-zero q and v entries, since we can get to state 14 from them, and from the last iteration v14 we know that it's 0.33. So after the first iteration we saw that 14 was 0.33, and after the second iteration we get a higher value for state 14, and then we get non-zero values for 13 and 10, and you keep on doing it until you get the appropriate way to get from the starting position to the goal position. So typically the agent does not have information on the state transition probabilities, as we have seen, and the agent doesn't know what the immediate rewards would also be. So it's all about learning through its own experiences. So now let's look into the third algorithm, which is SARSA. SARSA resembles QLearning. However, one difference is that QLearning is off policy and SARSA is on policy, and it uses the action performed by the current policy to learn the Q value. Here the update equation for SARSA depends on the current state, current action, reward obtained, next state, and next action. This observation led to the naming of the learning technique as SARSA, which stands for State, Action, Reward, State, Action, which symbolizes the tuple SAR S-A-, and in mathematical formula it would look as follows. Now, what are the practical applications of reinforcement learning? Where can we use reinforcement learning? So, reinforcement learning is quite widely used in building AI for playing computer games. AlphaGo Zero is the first computer program to defeat a world champion in the ancient Chinese game of Go. Others include Atari games, backgammon, etc. Reinforcement learning is also used to enable the robot to create an efficient adaptive control system for itself. If you look into DeepMind's work on deep reinforcement learning for robotic manipulation with asynchronous policy updates, that is a very good example of reinforcement learning. With some advantages, there are also some disadvantages that come. So now we're going to look into some challenges that come up with reinforcement learning. The main challenge in reinforcement learning lays in preparing the simulation environment, which is highly dependent on the task to be performed. When the model has to go superhuman in chess, Go, or Atari games, preparing the simulation environment is relatively simple. But when it comes to building a model capable of driving an autonomous car, building a realistic simulator is very crucial before letting the car ride on the street. The model has to figure out how to brake or avoid a collision in a safe environment. where sacrificing even 1,000 cars comes at a minimal cost. Transferring the model out of the training environment and onto the real world is where things get tricky. Scaling and tweaking the neural network, controlling the agent, is another challenge. There is no way to communicate with the network other than through the system of rewards and penalties. This in particular may lead to catastrophic forgetting, where acquiring new knowledge causes some of the old to be erased from the network. Yet, another challenge is reaching a local optimum, that is, the agent performs the task as it is, but not in the optimal or required way. For example, a jumper jumping like a kangaroo instead of doing the thing that was expected of it. For example, like walking. So that would be a great example of reaching a local optimum. And finally, there are agents that will optimize the price without performing the task it was designed for. So that was the end of this workshop. But before finishing, I would like to wrap up whatever we have learned so far in all the videos from MIST 101 and 102. So throughout the videos, we have introduced various concepts to you in a very simple and interactive manner. So some of the topics that we have covered would be introducing what AI is, and then finally getting into what machine learning is and the different types of machine learning, that is supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. And then within machine learning, we have another topic called deep learning, within which we talked about CNN, RNN, LSTM, GRU, and GANs. Apart from this, we also talked about artificial neural networks. So I hope it was a great learning experience for all of you, and thank you for sticking with us till the very end, and hope you all had as much fun learning as we had in teaching the concepts, and hope to see you all very soon. Thank you.